I'll flick to the next slide. So, as I said, it's part 2 tonight of life in the solar system. So tonight we're going to have a look at Europa, Titan and Mars and see what they might have to offer in the way of habitability. And then later on we'll have a look just very briefly at a couple of upcoming missions to Europa and Titan. And then finally I'll finish off tonight with a bit of a look at potential oceans in the solar system. So first though, I just want to recap a couple of important ideas from last month, in case anyone didn't see last month's talk. So last month we saw that life might have got started in warm ponds or hot springs or even tidal pools. And we saw the other option might have been these alkaline hydrothermal vents at the bottom of the ocean. These have tiny little pores which are about the same size as living cells and have a lot of similar properties to living cells. So they're an ideal place or candidate for where life might have got started on Earth. And we had a look at some of Earth's extremophiles. These are life forms that survive in or like or even require what we as humans would think of as very extreme conditions, and that includes extreme temperatures, radiation, salts, acidity, and the list goes on. And we finished off last time looking at Enceladus, and we had a look at what kinds of Earth life might survive in the ocean of Enceladus. And we found that Enceladus would be habitable for some types of Earth life, but with the reminder that habitable doesn't actually mean inhabited. So tonight let's start by heading back in from Saturn towards Jupiter, where we're going to have a look at Europa. Now Europa, like Enceladus, is an icy moon with an ocean under the surface, and it's a good candidate for life as well. And just go back there, and just for a bit of perspective where we are in the solar system, Jupiter and Earth, the closest they get together is about 590 million kilometres, which is just over half an hour of light travel time. So that's just an idea of where we are. So Europa is one of Jupiter's 4 largest moons, the Galilean moons, and it orbits here in relation to the other 3 Galilean moons. It's a little bit smaller than our moon, about 90% of the size of Earth's moon, but a lot bigger than the tiny Enceladus that we saw last time. So we know, first of all, that Europa has an ocean, and we'll have a look at the evidence for that soon. But what keeps it warm enough to stop the ocean from freezing? Well, Europa orbits Jupiter in a slightly eccentric orbit, which means it's not quite circular. It's a slightly squashed circle. That means that as it orbits Jupiter, it gets closer and further away, and so the gravitational forces of Jupiter across Europa are stronger at one point and weaker at another, and this results in a squeezing and stretching of Europa. And just like bending a piece of metal heats it up with friction, the internal inside Europa is heated up by the stretching and squeezing and keeps it nice and warm enough to keep the ocean liquid. Now that's obviously a very exaggerated animation from NASA, and quite hard to keep watching too long, get a bit seasick. The surface only goes up about 30 metres, so you wouldn't see it really, but it's enough to keep it warm inside. So Europa is differentiated, which means the materials inside it have been separated out due to gravity by their density. So we have iron core in the middle, surrounded by a rocky layer, then water, and then ice on the outside, the least dense. The ice shell itself is between 3 and 30 kilometres deep. It hasn't really been totally established how deep the ice shell is, how thick the ice shell is. Under that is a subsurface global ocean, which averages about 100 kilometres deep. Now, if you compare that to Earth's oceans, the average depth of our oceans is about 4 kilometres, that little tiny thin blue line there. And the deepest part of Earth's oceans is the Mariana Trench, which is nearly 11 kilometres deep, and that's that thicker red line there. So altogether, Europa has about twice as much liquid water as Earth has. You can see the tiny little Europa with the Earth beside it, and that difference in liquid water. And that's not including the ice. If you melted that, there'd be even more. So what is the evidence for an ocean, or for a global ocean on Europa? The best evidence is actually something called an induced magnetic field. And how this works is that Europa, when it's orbiting Jupiter, is passing through Jupiter's magnetic field. As it passes through the magnetic field, that creates a current inside Europa's saltwater ocean. And this current inside the ocean produces a secondary magnetic field, which is called an induced magnetic field. Now, the reason that the magnetic field around Jupiter is changing with relationship to Europa is that Jupiter's axis of its magnetic field is about 10 degrees off its rotational axis, and that means the magnetic field is moving around at an angle, and so at different points it's got different strength and different direction. But as well as that, as we saw before, Europa moves away from and closer to Jupiter during its orbit, so there's a second thing happening as well. The strength of the magnetic field relative to Europa is changing in the second way, and that means there's a couple of different things happening. And a little animation there just shows the two different components which are added together to give an induced magnetic field. You can see it's quite complicated, but this does mean that a future mission will be able to go to Europa, measure this induced magnetic field, and should be able to work out the thickness of the ice, the depth of the ocean, and how salty the ocean is, because it's the salt water in the ocean that's producing the currents to give this induced magnetic field. So it'll give a lot of information when we send a mission to there. In fact, Europa Clipper mission, which will be leaving in a few years, we'll have a look at later on tonight. And just like Enceladus, Europa seems to have plumes of water erupting from its surface. They're very few and far between, but you can see from these ultraviolet pictures from the Hubble Space Telescope in 2014 and 2016, just with the yellow arrows there, which are pointing to where the plumes are coming from, near the bottom and round the side there. So those plumes do show that there's some sort of cryovolcanic activity happening, so there's water coming up through the volcanoes. Obviously it'll turn to ice crystals pretty quick once it hits the colder space. But these could actually be coming from some pockets of water in the ice, that's a possibility, or it could be coming from deep in the ocean below, or possibly even both. Now we know that life on Earth needed, or did very well once oxygen was available, and that's when multicellular larger life appeared on Earth. So a question might be, is there oxygen in the oceans of Europa? It turns out that there actually could be. As you probably know, Europa is constantly being bombarded by radiation from Jupiter especially, but also some radiation from the Sun. This tends to break water molecules apart into hydrogen and oxygen. The hydrogen will generally disappear off to space, and some of the oxygen will add to Europa's very tenuous atmosphere. But it's possible that quite a lot of the oxygen could make it through the ice shell to the ocean below. And a couple of ideas that people have had is that one might be it'll hitch a ride with bubbles of very salty water in the ice, which will slowly make their way down to the ocean below, or maybe subduction, which is like ice sheets going under each other, just like tectonic plates on Earth. And so those are two methods which have been looked at and quite possible for a way for oxygen to get into the ocean below. It even seems that it could be possible from models that the amount of oxygen in Europa's ocean is the same amount or very close to what we have in our own ocean on Earth. Oceans on Earth. And what about those colours on the surface of Europa? Well, they're generally from a lot of sulfuric acid and sulfur compounds. A lot of the sulfur will come from nearby Io, which has about 400 active volcanoes. And it's close enough that a lot of sulfur will actually be making it to Europa and probably out to some of the other moons. But the salts and the minerals will be coming up from the ice and the ocean below. And in particular, this yellow region here, the Tara region, it's been shown that this yellow is actually normal table salt, sodium chloride, which means normal sea salt coming up from the ocean below. And it turns that yellow colour when it's irradiated. So that's more proof of a saltwater ocean in the, under the ice on Europa. So now we can say that Europa has a saltwater ocean and that it will be in touch with the rocky core below. So what does that mean? It means that it's quite likely that hydrothermal vents, which we saw are a way that life might be able to get started, alkaline hydrothermal vents are probably quite likely at the bottom of the ocean. And it's also quite possible that there's magma in the below the bottom of the ocean as well. And that means these other vents, such as black smokers, may also be there. And as we saw, the water from those can be up to 300 to 400 degrees Celsius, whereas the water from these is about 40 to 90 degrees. And so what that means in the end is that, yeah, there could be somewhere for life to get started on Europa, or could have been at the start. That's assuming that the hydrothermal vent idea is one way that life could start, which it does seem to be, but of course we can never know for sure. And it also means that there would be some warm areas and other nutrients for any life which may have formed on Europa. So let's have a quick look at what kind of microbes might survive there if we would take some microbes from Earth and drop them on Europa. We'd probably find that halophiles and cryophiles, which are the cold-loving and salt-loving microbes, would be quite happy. The temperature of the water is probably, or could be down to as low as -4 degrees Celsius, and so you'd want to be a cryophile, and probably quite salty, so you'd want to be a salt-loving microbe as well. And we know that there's a lot of radiation from Jupiter hitting Europa, so if anything was to kind of go up through the ice, you'd probably want to be a radio or radiation-resistant microbe or a radiophile. So it's possible that some radiophiles from Earth, if we put them in the ice, may survive. You wouldn't want to go all the way to the surface though, even if you were radiation resistant. I think you'd probably be, even a microbe that could resist a bit of radiation would be zapped and probably smashed apart by the radiation. And of course, if we have the hydrothermal vents at the bottom, then thermophiles would also be very happy living there. And we also had a look last time at some microbes that actually happily eat electricity, or I should say ingest electrons and electricity, especially when there's no other food sources around. They can get the energy just from electricity. So anything in the oceans may, who knows, may be able to live off the electric currents that are set up in there as well. Again, we'll probably not know until we can send something there into the ice and into the water and check it out, but it certainly does seem like it would be habitable for some life forms from Earth. Now, Europa is 4.5 billion years old, which is the same age as the solar system. And with that amount of time and with oxygen in the ocean, it may be possible that if anything did form in the ocean, that it may have had time to evolve into something larger. Now, these are actually some real life things from Earth. That actually looks totally fake, but it's actually from a video which was taken of some weird jellyfish. This one's a ping pong tree sponge, and this one is a carnivorous sea squirt. And so these are very weird creatures that are found on Earth. And so I'm sure that anything on Europa would probably be just as strange or maybe even weirder than what we've found in our own oceans. So all in all, I think it's possible that Europa could have microbial life, and it may even be possible for something larger to be there as well. Let's head back out again towards Saturn, and this time we're going to have a look at Titan. And again, just for some perspective of where we are in the solar system, Saturn is 1.2 billion kilometres away from Earth at its closest, which is about 67 minutes of light travel time. And looking closer at the system here, this is Enceladus that we saw, and out here at 1.22 million kilometres average is where Titan sits as it orbits Saturn. Now, Titan is the second largest moon in the solar system after Jupiter's Ganymede. It's about 50% larger than our moon, and it's even larger than the planet Mercury. So it's a fairly large moon, almost like a planet in itself. In fact, Titan almost seems more of a planet than Mercury does. But we can't see a thing on the surface of Titan in visual wavelengths because of that haze that covers the whole moon. But if we could remove it, we would be able to see some really interesting features on the surface. This was taken by Cassini space probe, mainly in infrared wavelengths. And so what are we looking at here? Up the top, these white streaks are northern summer methane clouds. So in fact, this is the northern summer of Titan, the North Pole up around here somewhere. So those are methane clouds, maybe about 20 kilometres up from the surface. And these are the three large methane seas and hundreds of smaller methane lakes. Down at the equator here is a desert region. There's actually deserts right around the equator with sand dunes. The deserts, though, are slightly damp underneath, so probably from methane drizzle and possibly from some previous flooding. And the last interesting thing here is something called Salt Crater. That's an asteroid impact crater, which we'll have a little bit of another look at later on tonight. It's a huge crater, about 80 kilometres wide, and is a target for some astrobiology that's going to be done in the next 10 years. So the layers of Titan, we'll just have a quick look at those. The atmosphere is about 600 kilometres high, which compared to Earth, we have about 100 kilometres is where space kind of starts above Earth. Titan's atmosphere, 600 kilometres, so it's pretty thick, pretty high atmosphere. It consists of about between 95 and 98% nitrogen and about 2 to 5% methane. Generally, if you kind of remember, about 98% and 2% is probably pretty close. The surface itself is made of normal water ice that's called Ice 1, and it's thought to be about 80 kilometres thick. Below the ice shell is an ocean of very salty water, and it will have quite a bit of ammonia in it as well. The salt content is possibly about 30% from calculations that astronomers have made, which is about the same as the Dead Sea on Earth. The ocean could also be up to 300 kilometres deep, and if it's that deep, if that's correct, it would have about 10 times as much liquid water as Earth's oceans all put together. And so that would be probably the biggest ocean in the solar system, the most voluminous ocean. And below the ocean, between the ocean and the core, is a very dense high-pressure ice called Ice 6, and in that the water molecules are packed a lot more tightly or differently than they are with ordinary ice, so it makes it more dense than water. And so just having a look again at the size of Titan with maybe 10 times as much water as Earth, it's quite an amazing amount of water. And that's, again, without the ice, so if you melted the ice as well and took that into account, there'd be a lot of water. So now that we've seen there's an ocean under the surface of Titan, the question is, could life have started there? Well, this ice layer could be a problem if hydrothermal vents are the way that life gets started. However, it's also quite likely that in the past Titan was warmer, had a thinner shell of ice on top, and that the ocean may have actually been in contact with the rocky seafloor. If that was the case, it is possible that there were hydrothermal vents there, and that life may have got started. It also depends on what the contents are of the rocky mantle, if the right rocks are there. But let's say that life could get started and that there was some life at the beginning of Europa's life. And maybe as it started freezing over a bit, the life managed to evolve to live in the ocean above. If that's the case, it's still possible that some nutrients could come up from the rocks through the ice layer at the bottom, maybe through convection or maybe cracks. And it's also possible that things may come through from the top layer. There's a lot of organic molecules and all sorts of molecules in the atmosphere of Titan raining down onto the surface. Now, C2H2 is acetylene, and it's quite a common molecule on Titan. And it's been shown that some microbes on Earth are acetylenotrophs or acetylene eaters. They get the energy from acetylene. And there's one in particular, if you can pronounce that, Pelobacter acetylenicus, which sounds almost like a fake name, but that's something that has been studied and can use acetylene as an energy source. So that shows that there's something on Earth that is an analogue for something which may happily live in the ocean there. But also, as I mentioned, it's very salty, could be 30% salt, and it's likely to be very, very cold, probably even colder than that, -4 degrees of Europa's ocean. So you'd also want to be a cold-loving and salt-loving microbe as well. Let's jump up to the surface now and have a quick look at what's happening up there. The surface of Titan is a nice cold -179 degrees Celsius. So that's so cold that water freezes as cold, as hard as granite. So where Earth has granite, Titan has ice. And it does have rivers and lakes and seas and rain, and as I mentioned before, these are liquid methane, which is a liquid around about those temperatures. There are also deserts, and so there's some sand dunes, or a picture of some sand dunes from NASA, kind of giving an idea of what they might look like. And we'll actually get some photos of the actual sand dunes in about 12 years' time, and I'll show you the mission that's going to have a look at that. So just like Earth has a water cycle, Titan has a methane cycle. So methane will evaporate, form clouds, rain, which will fill up rivers and seas, and then the cycle repeats. But as well as a methane cycle, there's something even more interesting happening. What actually happens is some of the methane can find its way up to the top of the atmosphere, very high in the atmosphere, and the methane will be broken apart by ultraviolet light from the sun in a process called photodissociation or photolysis. Now, the methane, when it's broken down into these other molecules, will form hydrogen, ethane, acetylene, and many, many other molecules. As well as that, some of the pieces of the broken up methane will react with nitrogen in the atmosphere and create complex organic molecules, literally hundreds of different types. And out of these molecules, the hydrogen, a lot of that will disappear off into space because it's so light, but a lot of it will also fall down towards the surface, as will a lot of the other molecules. Now, these four here that I've circled up here are particularly interesting, and we'll have a look at those a bit later as well. There's vinyl cyanide, and of course hydrogen and ethane and acetylene. So we'll come to those in a few more minutes and just see what's really interesting about those. So let's have a quick look at those seas I mentioned before. There are three large seas. They are Punga Mare, Ligeia Mare and Kraken Mare. And you can see the size of them just with New Zealand superimposed on the top there. So quite big, quite a bit of liquid in those. I think Kraken Mare from memory is about 400,000 square kilometres, and I think New Zealand is probably about 160,000 square kilometres, roughly around there. So the surface area, though New Zealand doesn't quite look right there, but with the sizes, but yeah, there's more surface area in Kraken Mare than there is in New Zealand altogether. Kraken Mare is methane sea, but probably has quite a bit of ethane in it as well, and Ligeia Mare is thought to be pretty much just pure methane. When it rains, it washes the methane or the ethane out down these channels into the other seas there. So talking about those seas, what sort of cell membranes might form in the seas or even the lakes? We had a look at these phospholipid molecules last time, which make up the cells of life on Earth. Now, it's interesting that the phospholipid molecules themselves, if you throw those into water, or a whole lot of them into water, they tend to form membranes because one side likes water and the other side doesn't like water. And the best way for the two ends of the molecule to get what they want is to form a membrane, which is great for cells on Earth. But on Titan, of course, these phospholipids would just freeze solid and be absolutely useless. And there was a bit of excitement a few years ago about this other molecule I showed before falling from the sky in Titan called vinyl cyanide. It was thought that these might spontaneously form a kind of a membrane in liquid methane, just like lipids do or phospholipids do in water on Earth. And if they did, they would have formed something called an azotosome, which would be a kind of a flexible cell membrane which would stay flexible even in liquid methane. Sadly though, a later paper in 2020 showed that it was possibly or probably unlikely that they'd spontaneously form these membranes. Although if they could be made to form a membrane, it still would be soft and flexible, but it doesn't look like it's going to actually form automatically. But then they said it's probably not a problem because life on Titan may actually not want to have a membrane anyway, or life on the surface of Titan, because it's so cold, reactions happen so slowly that a membrane may actually prevent nutrients getting through and would inhibit life. And so life on Titan may just be some sort of non-cellular life, should anything exist on the surface, and would probably just stick to the bottom of the ocean or bottom of the seas or the sides of the seas, would be pretty immobile and would just have to wait for food to come along. So that would be a very strange type of life, and I kind of wonder if we'd even know that when we saw it, if we ever sent something into the oceans. But if life had managed to form in on the surface of Titan or in the methane seas, what would it eat? Well, it turns out that some of the common molecules there, this one here, acetylene and hydrogen, can be used and produce as much energy as some chocolate, which is about 21 kilojoules per gram. Now also, just a bit of a warning, don't try to eat it yourself. Unless if you're a microbe on Earth that eats acetylene, you'll be fine, but wouldn't recommend for humans. The other one was ethane, and ethane and hydrogen can also be used as a bit of an energy source. Not quite as much energy, about 4 kilojoules per gram, but still energy nonetheless. So those are two possibilities for life on the surface of Titan. So there's an interesting thing happening on Titan. There actually is some missing molecules there. And it's probably interesting to kind of think of it as starting with chocolate. So if you put some chocolate in the cupboard one day and you came back the next day and found it had gone, you'd probably assume that someone had eaten it. It's probably the best assumption, especially since it hasn't been wrapped, just sitting loose in the cupboard. And it appears that with some studies they've shown that there does seem to be less acetylene and less hydrogen, also less ethane on or near the surface of Titan than expected from the amount that's being produced in the atmosphere and falling down to the surface. So the question is, could there be something that eats acetylene or ethane on the surface, some sort of life? It's a possibility. It's also possible that there's just some other chemical process going on. So it's one of those mysteries that may get solved with the mission which is coming up to Titan, which I'll talk about shortly. But it's an interesting thing to think about, that there could actually be something happening there. So let's come back in again, this time to Mars, and this is our last habitable or possible habitable place that we'll look at tonight. This is Mars as it is now, very dry and very cold and with a very little atmosphere. But there is a lot of evidence for liquid on the surface of Mars in the past. You've probably seen heaps and heaps of pictures of evidence of rivers and river valleys on Mars. An interesting one actually is this one here, which is a dried riverbed on Mars, where you can see pebbles that have been rounded by water flying in a stream, and about the same size analogue on Earth there. So two photos, one from Mars, one from Earth, showing that there were definitely streams and water flying, rounding the pebbles, but pretty obvious from all these river valleys what was happening there. But as well as rivers, there were also lakes on Mars. This is Jezero crater, and currently the Perseverance rover is working there, looking for signs of life and doing a lot of study there. Obviously very dry at the moment, very desert-like. But if you look at it from above, you can see that there was a river that used to flow into it very clearly, and a river delta where all the sediments had washed into the lake. It's quite a large delta here, and Perseverance is working around here somewhere, I think. Looking at it from even further out, you can see it's about a 45-kilometre diameter crater, so pretty large, a little bit bigger than Lake Taupo. And at the top there in our little white box, we can see the zoomed out picture of what we have over here with the river flowing in and the river delta.
To really bring this to life.
Let's go back, because I've got a little video here which just shows the formation of Jezero crater and its lake, and it gives a really good history of it with some really amazing graphics. It's narrated by one of the project scientists with the Mars 2020 rover, so I'll just play that now. It's only about a minute.
To really bring this to life and show us how this site came to be.
So here we are 3.8 billion years ago, and we're about to see the impactor that is going to create Jezero crater. So here it is speeding towards the surface, and boom, we have Jezero crater formed. Quite a catastrophic event, perhaps at a time when we had water on the surface. So here we have Jezero crater. It is now here in this landscape. And what we see now is we know, based on what we see from orbit and now on the ground, that water rushed into this crater from at least a couple channels on the crater walls. And here we see it filling up, and we have conclusive evidence that this crater did indeed fill up all the way to the brim. And we know that it actually overflowed. And there aren't that many craters on Mars where we can say that. And so we know that there was water in this crater for geologically significant amounts of time. And here we see that outflow channel. And as we zoom in here, we're going to see over time, of course, that lake dried up. It disappeared, and eventually it leaves us with the fossil landscape that we have to explore with the Perseverance rover today.
It really explains quite well what happened there. So that's just one of the many lakes that existed on Mars in the past. And so Perseverance rover, as I said, is working through in that area. It has been drilling some of the rocks and getting samples out which are going to be sent back to Earth in a later mission. But it has managed to find organic molecules in the rocks and in the dust around the rocks as well. Not necessarily from life, but it could be. But these molecules can be made by physical processes as well. It also has taken some pictures of sedimentary rocks near the river delta that we saw before in the previous slides. This picture here was actually only taken about a week ago, so it's pretty up to date. And so these stacks of sedimentary rocks are great for looking at climate history of Mars and also the habitational or the history of habitability on Mars. May even have some fossilized microbes in them as well. And you can actually look on NASA's website and find heaps of these interesting pictures as well. And as I said, it's actually collecting some of these samples to be sent back to Earth in a later mission. What's actually going to happen is they're going to send a module up to Mars, and it's going to land on Mars, collect some of the samples, then it's going to launch its own rocket up to orbit Mars. That rocket is going to drop off a little capsule which will orbit Mars, then another ship will come along, pick it up, and then bring it back to Earth. So it's quite a complex process. Seems like lots could go wrong, but I'm sure there'll be testing that a lot before it goes up. So we'll actually have some Mars samples on Earth to look at and see if there's any fossils of ancient bacteria or microbes. So Mars not only had lakes and rivers, but it had a substantial ocean in the past. This ocean covered about 20% of the surface of Mars, and it actually contained more water than Earth's Arctic Ocean. The amount of water in the ocean was enough to cover the whole of Mars to 130 metres or more, but of course the water will flow into the lower regions, which just happens to be in the northern hemisphere of Mars. The deepest part of the ocean is over 1.5 kilometres deep, and the ocean itself persisted for at least 1.5 billion years and possibly up to 2 billion years. And so what's the evidence for that ocean? Well, some of the best evidence for the ocean on Mars actually comes from tsunamis. Some of them caused by landslides and some of them caused by asteroid impacts. And this one, Lomonosov crater, is really interesting in particular. That's the crater there now. It's about 120 kilometres diameter. Now, the tsunami that was caused by the asteroid that hit the ocean, creating Lomonosov crater, has left some telltale signs that allow us to date the ocean at the time of the impact. So down at this little area here, we can see this thumbprint terrain, they call it, and this is evidence of a tsunami that has washed up from that direction, pretty much that same direction, and has left this thumbprint terrain. Now, interestingly enough, the age of the crater can be determined by the number of craters inside that crater, since it was formed, as well as the degradation, and it puts the age of the Lomonosov crater at about 3 billion years ago. This tsunami evidence here has been dated also to about 3 billion years ago, again from counting craters. So pretty much good evidence of a tsunami caused by an asteroid that created that crater 3 billion years ago. And a little bit more evidence there, just further along down here. You can see some channels or some grooves which have been formed by the water as it rushed out after the tsunami, and a large number of boulders which were washed down as well as the tsunami ran out back to the sea. So that shows that the ocean would have been 1.5 billion years old at that time, roughly, and was probably still quite substantial, so it could have lasted for another 500 million years. And so the ocean itself could have lasted for 2 billion years. That's more than enough time for life to have appeared on Earth, and so why not on Mars as well? Certainly gives it a good chance. I'll just sit past those. Now, we saw also about life possibly starting in hot springs or tidal pools on Earth, and there are definitely is evidence of hot springs on Mars. This one here is about 100 metres, not too different to the Grand Prismatic Spring in Yellowstone. So we can safely say that there were hot springs on Mars, and there were probably these deep sea hydrothermal vents as well. So the two options for starting life were actually available on Mars. Of course, there'd be no tides on Mars, as there was no large moon, unless there was a large moon that we don't know about. And so tidal pools evaporating and refilling with high tide probably wouldn't be an option. But we have these other options, so it's pretty likely that life could have started on Mars just as easily as it did on Earth. So then the questions are, first of all, could life have formed on Mars? And we saw yes, possibly could have. Could it have evolved to become resistant to radiation? Well, that's quite possible as well, as it did on Earth in some places. And could life still be on Mars or under the surface today? So let's have a look at that. The atmosphere of Mars is very thin. It's less than 1% or about 1% of Earth's atmosphere, made mainly of carbon dioxide with some nitrogen, argon, a bit of oxygen and a bit of carbon monoxide. It's not protected from radiation as it hasn't got a magnetic field to direct particles away or much of an atmosphere to protect it from ultraviolet. The soil itself contains a lot of really nasty salts called perchlorates, as well as other things, iron oxides that give it the red colour, hydrogen peroxide and a bit of ice. These perchlorates are thought to go down maybe as far as 30 centimetres under the surface. And that's a bit of ice, bit of proof of ice by the Phoenix Mars lander that scraped a bit of soil away. So if there are microbes that survived, what would they be like? Again, you'd probably want to be a polyextremophile, which means you want to be able to handle cold, very low water conditions, radiation, and you'd want to enjoy salt, especially perchlorate. It does turn out again that there are some life forms on Earth that have been tested that can, very few, but that can live off perchlorates and carbon monoxide. So that's great because we know there's some carbon monoxide and some perchlorates on Mars. So it looks like there is a chance that something could survive there. So let's now have a look at a couple of the upcoming missions to Titan and Europa. It's a very quick overview. The first one is NASA's Europa Clipper mission, which of course is going to Europa. That will launch in a couple of years' time and will arrive at Europa in about 2030. Its goal is not really to detect life, but to check to see if Europa is habitable. And that means it wants to see if the chemistry under the ice may be suitable for microbes. It'll also find out how deep the ocean is, how salty it is. As we saw earlier, using induced magnetic fields will help with that. And also to have a look and see what might be able to make it through the ice to the ocean, providing other molecules from the surface. So generally, it's a mission to look for habitability rather than to look for life. The other NASA mission I want to talk about is the Dragonfly mission to Titan. Now that one leaves in 2027 and arrives 7 years later. Dragonfly is a very large octocopter drone. It'll be dropped into the atmosphere and protected by a heat shield. As it slows down, it will deploy a parachute, and then once it gets still a fair amount of height above the ground, it'll release the drone, which will start its rotors up and make its way down to the surface. You can see the size of a person there. It's about 3 meters long, so it's pretty huge. But the atmosphere on Titan is so thick that flight is really easy, even easier than on Earth. And also with 1/7 of the gravity as well. So the mission itself will last up to just about 3 years, and through daily flights, Dragonfly is going to be looking for chemical biosignatures amongst other things. So this mission actually is going to see if it can find any signs of life on Titan. The ultimate destination of Dragonfly is Salp Crater, which we saw earlier. Now Salp Crater was produced again by an asteroid impact. It was a few 100 million years ago. The impact itself would have melted a lot of the ice and would have left liquid water there for maybe tens of thousands to a few 100,000 years. With the mix of energy and water and organic molecules from Titan, that leaves the opportunity for maybe something more complex to have formed, possibly even life. And they are actually going to be looking for any signs of life that could have formed in that crater. The fact that it's a fairly young crater and also apparently relatively unaffected by weather means any life or any complex molecules that form there would obviously be very frozen solid, but also well preserved, and it makes an ideal place for Dragonfly to head to have a look and see what might be there. So it's almost like a little laboratory of ancient Earth to see what can happen. And again, I've just got a little video which explains the science of Dragonfly quite nicely. It's just a couple of minutes, this one.
Saturn's largest moon, Titan, has a thick atmosphere and a frozen surface rich in organic molecules. In 2034, a NASA mission called Dragonfly will arrive at Titan and study its chemical makeup. Dragonfly is a rotorcraft designed to visit multiple sites across the moon's varied terrain. At each new landing site on Titan's surface, Dragonfly uses a pulsed neutron generator and onboard gamma-ray sensor to detect key elements such as carbon and hydrogen in organic materials or oxygen in water ice. Dragonfly determines if there are well-defined layers of these materials just below the lander. For a closer inspection, Dragonfly uses its drill to generate tailings from Titan's hard, frozen surface. These surface samples can then be ingested through the pneumatic system, carried with Titan air into the chilled sample lines and to the sample collection carousel. One of the carousel sample cups is placed in a pneumatic port. The cup captures the surface material from the cold air stream and transfers it to the chemical laboratory for measurement. Pulses from a laser release large organic molecules from the surface sample for analysis in the mass spectrometer. The mass spectrometer sorts molecules by mass and measures diagnostic fragments that tell Dragonfly the kinds of chemical components that are present in the surface and whether there are molecules of prebiotic interest. For those potential prebiotic samples, a new cup is placed into an oven and heated to release molecules into a gas chromatograph, where they are sorted for size and type before entering the mass spectrometer. This advanced separation of organic components includes isolating molecules with the same formula but different chiral arrangements, or handedness. Having a preference for one-handedness over another is a key biosignature for life on Earth. When the chemical analysis is complete, Dragonfly may choose to take another surface sample or find a new location on Titan to investigate.
Complicated science, a complex science going to go on there. So we should get some amazing results back from that, but also some streaming video. They're going to stream video back from Titan. There'll be a lot of very high definition photos as well, so it'll be pretty amazing to be able to watch that. So I'll just finish off tonight with a bit of a look at some of the other possible oceans in the solar system. There could be more than 10, maybe up to 14 oceans now in the solar system. First of all, at Jupiter, we saw Europa earlier, but Ganymede and Callisto are also good candidates for oceans. Again, from induced magnetic fields, it's pretty certain that there should be some sort of liquid water in these two moons. Ganymede may actually have layers of oceans in between layers of ice, or one thick ocean. That'll be another mission called JUICE, which is heading that way, leaving next year, I think, and arriving also about 2030, which will actually study Ganymede in particular and may be able to give us some answers there. Callisto's ocean is probably very thin, but it's probably very salty and with a lot of ammonia. The reason being that it's not differentiated and won't have much heat coming from the core, and if it has got an ocean, it must be fairly salty and have quite a bit of ammonia to stop it freezing. Now, Enceladus that we saw last time here, we saw that there's another moon out here called Dione, and that Enceladus and Dione are in a 2-1 orbital resonance, which means that for every one orbit of Dione, Enceladus does 2. And this means that they both give a little tug on each other regularly, and this in turn stops the orbits from being circular, and like we saw with Europa earlier, it means that it will lead to a bit of tidal heating and keep the interior warm. So gravity measurements and modelling of Dione seem to show that that should also have an ocean maybe 30 kilometres or more deep under a thick layer of ice of about 100 kilometres. It also seems from modelling that the ocean should be in touch with the rocky floor, so that gives Dione a chance of actually having a similar kind of chemistry and possibility for life as Enceladus. The ice, unfortunately, being 100 kilometres thick may make it almost impossible for us to ever verify that, but it does seem to be a second ocean just in near Saturn. Out at Uranus, there are 5 moons which seem to have signs of resurfacing, which in turn are signs of cryovolcanoes, which means water coming up from an ocean underneath, resurfacing the surface. And so that's a little bit of evidence for these 5 moons. So they're of interest too for looking for oceans in the outer solar system. And perhaps the most surprising ones might be Pluto and Triton. Triton is the largest moon of Neptune, and it has a very young surface, less than about 10 million years old, which is pretty young. This would appear to be from water coming up from underneath and covering up the craters, so that when you count the craters you can generally tell how old a surface is, but the number of craters seem to show that it's only 10 million years or less old. So that's one bit of evidence of an ocean on Triton. It seems to also be that because Titan's on an inclined orbit, it's a fairly circular orbit, but it's inclined, which means that as it moves around Titan, the gravitational forces are pulling different parts of Titan. So it also gives it a tidal heating, but this one is from something called obliquity tides, which is the angle of the orbit. It's also quite possible that radiogenic heating from the core is keeping the inside warm as well. So there's definitely quite a bit of evidence for an ocean on Triton. I think probably the most surprising one is Pluto, though. You wouldn't think something so far out in such a cold part of the solar system could have any chance of having an ocean. But there are a few clues. So Pluto and its large moon Charon are tidally locked, so they both have the same surface, same face, facing each other the whole time. When that happens, it's generally will be that a more dense area will either be at the back or the front of the line joining the two bodies. Now with Pluto, this basin called Sputnik Planitia is directly opposite Charon. And so that would appear to be a more dense area. Now, because it's a basin, there would seem to be less stuff there, so you'd think it would be less dense. But it could be explained if there is a pocket of water under there which is more dense than ice. So it's likely there could be a pocket of water under there or a global ocean with more water in that particular part of it. Other clues are that Pluto was probably hotter in the past. So it probably started off as a very hot body and then cooled down over time. And that comes from the fact that the craters seem to all have expanded as if water had been freezing underneath, but there's no sign of anything going the other way, so that there's no sign of water. So what I'm saying, it was freezing, of actually melting again. So the idea is that it only seems to have been cooling down and starting off hot, which means that there seems to be evidence of an ocean at the start. The heat source could be radiogenic heating, which means heat from the core. The core is very small, and so any radiogenic heating would be very minimal. However, the ices around Pluto would be great insulators, so even a minimal amount of heating from the core could actually still stay within Pluto and could actually keep things nice and warm to produce an ocean, or to keep the ocean or part of an ocean liquid. So with that, if we now consider that there could be 14 objects in our solar system with oceans at the moment, and that's just one solar system around one star, with 300 to 400 billion stars in our galaxy and an estimated possible 6 trillion galaxies in the observable universe, that could be 2 trillion stars. And with, even if we said maybe an average of only 5 oceans per star, that could still be 10 trillion oceans in the observable universe. And I think that pretty much means that there must be something else out there, even if it is a lot of microbes, maybe something larger. That's something to think about. And that brings us to pretty much the end. So just in summary, we had a look at Europa, which we know has got a subsurface ocean. We looked at Titan, which also has a subsurface ocean, as well as surface seas, lakes and rivers of methane. We looked at Mars and can see that it used to have an ocean and lots of rivers and lakes. We had a look at the 2 missions upcoming to Europa and Titan, and the potential of many other oceans in the solar system and the whole universe, in fact. So that brings us to the end of tonight's talk. Thank you all for coming along. So if anyone's got any questions, I can't.
Europa pulsating by Jupiter. Is there will there be like an earthquake on the surface?
So Europa takes 85 hours to orbit. So it's just, in real life, it's actually very slowly moving up 30 metres and then down. So that was a very sped up animation by NASA, almost overly sped up.
So you wouldn't notice anything, in other words?
You probably wouldn't, not over 85 hours. I guess you could notice some Europa quakes, I guess.
No real shaking.
No real shakes, they'll be pretty gentle, yeah. Any other questions, or did I answer everything in the talk?
Question from the internet.
Oh, yes.
Is why do a lot of candidate planets or satellites, why are they full of methane?
Why are they full of methane? Oh, further out in the outer solar system. Yeah, it's because of the density of methane. Essentially, the inner planets are so close to the sun that any methane would have just been evaporated and would have been essentially blown out to the outer solar system. And the further out part of the solar system, it's past the snow line for methane and can actually become a liquid and remain on the surface. So essentially it's the temperature further out in the solar system that allows the methane to remain out there.
Is it known how long ago Mars's water oceans disappeared?
It's not certain, so we could see that they lasted at least 1.5 billion years. It's possible that it wouldn't have been much more than 2 billion, so maybe between the 1.5 and the 2 billion year time. And that would have happened as Mars lost its magnetic field, which of course let the solar winds rush through and brush off the atmosphere. And with
2 to 3 billion years ago.
2.1 billion years ago. Yeah, so that's about the estimate of time, isn't it? So that fits in quite well with the ocean. So maybe the ocean 2 billion, and then the atmosphere disappearing over that in 2.1 billion years ago. Pretty much nothing from then on. No more questions?
All right, John. Cool. Thank you very much for coming all the way up.
Thanks.
And